It starts in winter air thick with crosswinds and static. A ghost cloud drifts, radars hesitate, and 5 drones ride the wind, until NEBO M wakes up and rips the sky open. That's where the story turns. We'll go minute by minute. The AI's 90-degree bank, the throttle drop to cool the engine, the decoy pod that dupes a seeker, and the reignition that puts the team back on course toward Veshkaima's 500 kilovolt lines, and the blackout payoff. Before we move on, please take a moment to subscribe to the channel and like the video. Why did 5 cheap airframes cross a defended border in midwinter without lighting up every alarm? The answer starts with the weather report. Crosswinds at 35 to 45 miles per hour. Dense, cold air that carries radar better but also stacks clutter low. The route was plotted like a railway timetable, hugging 80 feet above the ground, threading ravines and frozen hedgerows toward the Veshkaima 500 kilovolt corridor. Before the first waypoint, a canister unlatched and seeded an aerosol ghost cloud, fine particles tuned to sit in that cold layer and lower contrast. Not a blanket. A moving fog bank that nudged returns toward uncertainty and forced operators to second-guess the blips near the tree line. On older sector radars, the screen didn't pop with clean tracks. It smeared. Snow patches, iced roofs, and ground scatter swelled as the aerosol mixed into the boundary layer. Techs tagged anomalies but couldn't get a stable lock, and they knew a higher-end system sat in reserve. That's the key. This cloud was a timer. It wasn't built to stop a modern array. It bought minutes, not immunity, holding the gate ajar long enough for the formation to reach the next line of cover. The Windweaver cascade worked in 2 parts. First came deception. Stage the cloud in front of weaker sensors and force their filters to lean conservative. Second came physics-aided flight. Each drone's control surfaces made thousands of tiny corrections a minute, not to hold a straight line, but to surf the crosswind. When the gust pushed, the onboard logic yawed, banked, and trimmed to convert lateral pressure into forward bite, keeping throttle within power margins. Instead of fighting the air, they harvested it, riding the same gusts that usually burn fuel reserves dry. Aerosols can degrade radar in subtle ways, especially in cold, humid air. They alter backscatter, shift the signal to noise ratio, and thicken the soup of returns close to the ground. That doesn't turn targets invisible. It reduces confidence. Operators see more low-level flicker, fewer crisp tracks. The limits matter. Particle size, humidity pockets, and mixing height change minute by minute. In some bands, the effect is mild. In others, it's enough to push a small signature below a threshold for a few crucial scans. Now set that against the drone's radar cross-section. Small bodies, composite skins, minimal metal. At 80 feet, the radar sees them against a messy winter floor. Snow drifts, scrub, fences, corrugated sheds, and frozen soil that reflects unevenly. Wind shear adds jitter to the path, which sounds bad, but at distance it blends motion into terrain shimmer. Low altitude and rough ground make movement look less like a target and more like background trying to stand up. The energy math decided the route as much as any map. A straight run at high throttle would die 90 miles short. By trading speed for range, the AI trimmed fuel burn and let the wind carry part of the load. Cruise airspeeds dropped, endurance rose, and the formation hit each timing window without draining the tanks. The risk was drift. The fix was micro-correction. Constant angle tweaks that kept power draw steady while the ground track knifed between towers and gullies. As the ghost cloud drifted past sector radars, screens showed motion without shape. A few calls went up the chain, but the lane stayed open. No missile launch, no intercept order, just a colder tone in the ops room and a note to wait for better data. The clock kept moving. The substation grew from a dot on a map into a set of coordinates with margin to spare. That's the takeaway from the first leg. Weather plus a staged aerosol can delay detection long enough to slip past the tightest ring of legacy sensors. Then the ghost peels off with the wind, and the standby array spins to life. NEBO M wakes. The easy part is over. How do you make one of Russia's most powerful radars see movement, then lose it without jamming? Start by letting it win the first look. The NEBO M spun up as the aerosol drifted out of the corridor and the display stopped smearing. Tracks snapped into shape as airborne infrared scouts cued ground returns. A Pantsir battery slewed its turret and fed coordinates into the fire control loop. The window for ambiguity closed fast. A direct intercept looked certain. The lead drone, running warmer after the crosswind push, threw a clean thermal plume. Seeker heads like bright, stable contrast, and this one offered it. Ground crews read out range and azimuth. Guidance lines tightened. At this point, brute speed would only sharpen the Doppler picture and burn fuel the formation couldn't spare. The AI didn't sprint. It turned 90 degrees across the beam. Perpendicular flight slashed radial velocity, the one number Doppler loves most. Closing speed fell toward 0, and the return slid down into the noise where slow ground clutter lives. The radar still saw a physical object, but its motion looked like a fence post in the wind. Tracking software ranks threats by how fast they approach or recede. Lose that vector and you drop in priority. That is the backbone of Doppler. Radars measure frequency shift from motion toward or away from the antenna. Big positive shift means closing. Negative means opening. Near 0 means the algorithms treat you like you're barely moving. Velocity gates filter out that low band to keep screens clean, especially near the surface. By flying sideways to the beam, the drone rode those filters, not by magic, but by math. The Russian crew didn't switch off. They paired a shot with an infrared track to hedge the radar drop. The missile left the rail with a seeker tuned to heat. The counter came in 2 moves. First, a throttle drop. Less burn, cooler exhaust, dimmer plume. Second, the winter ghost mode pod lit off under the wing, burning at a calibrated temperature that matched the engine's spectral signature in cold air. For a few seconds, the seeker saw twins. 2 near-identical heat points, one real, one synthetic, separated by just enough angle to force a choice. The drone went into an unpowered dive, trading noise and heat for glide, while the decoy held steady brightness to look like a stable aim point. The missile bit on the ghost and slammed it into a bright burst the ground team read as a kill. The lead airframe survived the near miss. With distance opened and the seeker fooled, the engine reignited, power came back on, and the drone climbed back into the approach profile. Sensors on the NEBO M regained a contact, but the window they needed had shrunk. The 90-degree bank had already clipped the radar's confidence, and the thermal trick had reset the intercept timeline by precious seconds. Not all of them made it. One drone, lagging the turn and carrying a weaker decoy, caught a fragmenting blast and went down. It wasn't random. The formation accepted the loss to keep a corridor open. The remaining 4 rolled their clocks forward, matched the terrain mask to the next ridgeline, and held the lateral track that the perpendicular run had cleared. That mid-mission duel didn't hinge on brute force. It came from timing, geometry, and heat control under pressure. With NEBO M's net behind them and the Pantsir cooling its tubes, the team pushed back to cruise throttle and rode the last crosswind toward the high-tension towers. The 500 kilovolt lines drew closer, and the blackout moved from theory to schedule. The duel didn't hinge on mass or top speed. It turned on timing windows, air density, Doppler geometry, and split-second decisions that kept sensors guessing and missiles late. That's the battlefield now. Brains over bulk, leverage over brute force. Outcomes set by how well you read physics under pressure. If you want deeper breakdowns of electronic warfare and the tech reshaping modern fights, subscribe. Drop your take in the comments on how AI will bend air defense next. Next time, we'll test whether this playbook holds when crews tune filters, tighten velocity gates, and teach seekers to spot the winter ghost's tell.